So first, let me discuss what is an orthogonal matrix. An orthogonal matrix, first it must be a square matrix where the transpose of the matrix is equals to the inverse of the matrix. Okay. One of the advantage of an orthogonal matrix. Okay. If A is an orthogonal matrix, the inverse of the matrix will be equal to the transpose. Since A inverse is equals to A transpose, so A transpose or A transpose A will be equal to an identity matrix. So if A is n by n matrix square, orthogonal applicable only for a square matrix. Okay. Then the following are equivalent. A is orthogonally diagonalizable. Okay, so if A is orthogonally diagonalizable, so A has an orthonormal set of n eigenvectors. Okay, orthogonal we will use Gram-Schmidt process. Okay, and then we can convert orthogonal to orthonormal set of n eigenvectors. Last one, A is symmetric. Okay, so what is symmetric? Symmetric is A transpose equals to A. So if A transpose equals to A, so A is orthogonally diagonalizable and A has an orthonormal set of n eigenvectors. Okay, A n by n, so there are n eigenvectors. Okay, next, what is similarity? Okay, so let's say we have two matrices A and B, both are square matrix. We can write B is SP inverse AP. Okay, so if B can be written in this form, B is similar to A. Why we need to find the diagonal matrix of A, which is D? D is equals to P inverse AP. Based on this definition, D is similar to A. Okay, so what is similar? Okay, so this is the reason why we need to find D. Okay, all elements in D are 0 except for the diagonal. Generally, element in A is non-zero. Okay, so why we need to find D? Okay, because D is a simple representation of A, and D is similar to A. It is similar in terms of first determinant. Okay, P inverse AP is D. This D. So A and D, okay, D is P inverse AP. A and D actually have the same determinant. Okay, so this is the first similarity. And then invertibility. Okay, A is invertible if and only if D is invertible. Okay, rank, A and D have the same rank. Okay, and then nullity, A and D have the same nullity. Okay, trace, A and D have the same trace. Characteristic polynomial, A and D have the same characteristic polynomial, which is the equation of lambda. Eigenvalue, eigenspace dimension. If lambda is an eigenvalue of A, and then the eigenspace of A corresponding to lambda and the eigenspace of D corresponding to lambda have the same dimension, number of bases in the eigenspace. Now, what is orthogonally diagonalizable? So, if A and B are square matrices, okay, so we say that B is orthogonally similar to A. If we can write B equals to P transpose AP. P transpose is equal to P inverse. So, B is orthogonally similar to A. So, P is the orthogonal matrix. Okay, if A is orthogonally similar, if B is a diagonal matrix, A is orthogonally diagonalizable and P orthogonally diagonalizes A. Orthogonally of eigenvectors. If A is a symmetric matrix, A transpose equals to A. Eigenvalues of A are all real numbers and then eigenvector from the first eigenspace and the second eigenspace are orthogonal. So now, how to orthogonally diagonalize A? Find a basis for each eigenspace, Gram-Schmidt process, to obtain orthonormal.